I would like to welcome you on your own alma mater. Peter here, he is also a PhD. You have one PhD. You are doing the second PhD now, or you're just the...
I just got it Tuesday.
Oh, really? So congrats. Peter will tell us something about outliers and mastering LOF detection. I'm not sure, I'm not in the domain, so please explain it to us. And I'll give him a warm welcome, please.
Thank you. So this talk is about mastering local outlier factor detection. If I may ask you, would you please raise your hand if you have worked with any kind of anomaly or outliers, except of deleting them from your dataset when you're trying to make any models? Nice. So if we have some beginners here who just got into machine learning and trying to work around the data, then you can find many datasets or almost all of the datasets which contain some outliers, which are created either by measurement errors and faulty data collection processes, either from events, sensors, or they've just been handled in the wrong way. There is a difference between measurements which are, so to say, useless for our main goal or main use case on which we want to create a model. So this is kind of a classification approach, but we don't want to classify majority groups in the sense of label data. Local outlier factor is an unsupervised machine learning approach where we can detect outliers, either the local ones or the global outliers. And I want to show you some use cases later on where we can apply it on a real-world use cases. So you can try and play with it a little bit. And we also have a hands-on exercise where I will show you how to use it on scikit-learn. So if we take it to the terminology level, local outlier factor is a machine learning algorithm that is commonly used for anomaly detection. It works by assigning an outlier score to each data point in a dataset based on its local density compared to its neighbors. What does that mean in reality? We have many data points, and we want to check what is an outlier. But we can calculate it with many algorithms or many approaches. Local outlier factor uses density. This is just a shallow algorithm, so it does not use any neural networks, and it's a pretty simple math, so to say. We calculate the density between data points in a data plane. If the neighbors or the density is low, then that is an anomaly. There is a difference between setting anomaly scores for detection of outliers which are far away from the majority group or the majority groupings. And those may indicate some issues with data collection, but there are outliers which are near to the main distribution, and they are just local outliers, and they just indicate slight changes in behavior. The local outlier factor algorithm on scikit-learn utilizes many hyperparameters. The main ones for us are the number of neighbors, which indicate how many data points relative to the data point from which I'm trying to detect if it's an anomaly we have to look for. So if we set the number of neighbors to 3, we are looking for the nearest 3 neighbors around us, and we look for the density and the distance between those data points to us. That is our key metric when we want to look into the data set where the data points are of different amounts. If we have a higher number of data points, we can increase the number of neighbors. Or if we want to create a more sophisticated or a more concrete local outlier factor model, then we can increase the number of neighbors, and regarding that, we will have higher densities. It all depends on the parameters where you want to detect the amount of anomalies. We have commonly, until the scikit-learn library version 0.2, the attribute which is called contamination was set to 0.1, which represents that the 10% of the dataset will be anomalies. After this update, it was changed to auto, so it will calculate based on the amount of data points. It is also dependent on the relative density of the data, how much anomalies we want to find. We can set it manually, but that is very use case specific if we have the task on to which we want to set up the data points. If we need to find anomalies, then we have to send the contamination higher. In my experience, outlier factor algorithms are used when we have a concrete use case and we know what to find. It is a lot easier if we have a use case or a problem already stated and we don't have to look for the problem itself. If you are looking into the data points and you have to find something or the anomalies by yourself without any domain knowledge, I recommend using 0.1 or 0.2 as a setup for this parameter, because it will give you some insight where the anomalies are, and it will give you more the global outliers. The higher the setting of the contamination, the more outliers we will gain. So that means if we have a majority group in the data groupings, it will gradually come to an anomaly state instead of being a normal distribution, or by the terminology of the local outlier factor, it would not be an anomaly. Then we have the novelty. If we use this algorithm, we can set it up to two settings. We can take the data in the meaning of, okay, I have the model trained, I know what an anomaly is. I get a new data point, we look at it, we detect, okay, this is an anomaly. We can use this approach in the manner of, okay, we have a set ground and we will just look for new anomalies or new data entries. That way, the model won't learn. But if we apply the novelty to the Boolean setting of true, then we will add the new data point to the measurement pool, and it will be set into the measurements as, okay, we have this data point. That is great if we have models for some time periods, but if we have a low dimensionality data, which is a kind of a finite grid, let's imagine a 500 times 500 x and y axis, and if we gradually add more data points to it, it will be so saturated that nothing will be an anomaly anymore, or it will be very low based on the contamination values. Therefore, I recommend, if you are using this approach and you are working with some kind of time series data, and you know that the behaviors will change gradually, then in some time periods, it is recommended to retrain the whole model and leave out the old data points. But it's also dependent on how much data you have and what do you want to achieve. If you want to follow approaches like behavioral trends, I recommend retraining the model on newer data, if you have it. That is today also a big problem with it. Okay, and we have number of jobs. That is classically the parallelization of the training approach. And the p-value would be the last one. It is the main measurement to calculate the distance between the data points. If we have those numbers of neighbors set, let's say 3, then we have approaches, or the p-value, which is an integer set to calculate the distance between the data points. It is commonly known as the Minkowski metric, and if we have low dimensional data, we can use p-value 1 or p-value 2. P-value 1 is the Manhattan approach, or the Manhattan distance, also called as the taxicab distance or the block distance. It calculates the sum of absolute distances along the axis. The Euclidean distance uses a straight line, so imagine the Manhattan distance, but you get the distance by the Pythagorean theorem within the straight line from one data point to the other. The approach chosen is relative to the dimensionality of the data. In this model, you can set either one dimension of data or multiple ones. It all depends on the use case and what you want to achieve. If you have a low dimensional data, I would not recommend using a p-value above 2. The results will only get worse. If we take a look at this plot, we can see that the relative data point x, which is on the coordinates 5, 5, we chose here two approaches, the Manhattan and the Euclidean distance. You can see that the relative amount or the relative distance is very different. Because if we take a look at the bottom left data point, which is on the coordinates 2, 3, the distance is 5 because of the taxi cab approach. If you have multispatial data, it would be a little bit hard to represent it on these plots, but you have to consider the curse of dimensionality. So it's not very useful to add there too many data dimensions because the distances will be too great and you will have a large amount of outliers if you leave the setting of contamination on auto. The dimensionality of space will be too big and the anomalies will be everywhere. After this algorithm finds those distances, we apply two approaches, relative distance and local relative distance, reachability distance, sorry. Reachability distance is the maximal distance between one data point, which was the x, and the kth or the end neighbor chosen within the training period. After that, if we inverse it, we get the local reachability distance, which is just an inverted value of the local reachability distances for that measurement data point. In simple terms, we have a big grid from data point 1 and data point 2, and they are created circles. We can imagine it as a data point of circles, and each neighbor has a certain distance to it. It is averaged and inversed, and by that, all the data points in the measurement window or in the measured space have a certain size. And based on that size, we classify if it's an outlier or not. If it's not meeting with its neighbor, then it's an outlier. And the LOF scores are calculated by 1 and minus 1, minus 1, if we use the classifier. Everything above 1 is not an anomaly, below 1 it is an anomaly. You can also use attributes as a negative local outlier factor if you want to use multiple labeling systems, because if the lower the number of the local outlier score factor parameter, the bigger the outlier. So if you need something more than binary classification or binary selection of is it an anomaly or is it not an anomaly, you can set manual thresholds and just relabel your data, because the model has each score within itself. You just take the scores out and relabel it yourself, then you can visualize it within big anomaly, global anomaly, local anomaly. It depends on the use case which you are using it. As I mentioned, there are density issues. So if we have the distribution of the data that 2% of the data is 2% of the data are outliers, it is easier to find it. But if we increase the amount of outlier densities, then it's slowly becoming a subgroup. I want to say with this that if the external group of outliers is getting bigger and bigger as the trends are changing, then it's not an outlier anymore, but it is a different state of behavior of the data. We can imagine that, okay, we are going at lunch at 11, always, but somebody put a new meeting there at 11, so we have to go at 12. So as the data points increase, the data in the density of the new lunchtime increases, then it's not an anomaly anymore, but it's a new reality, and the old data points slowly become obsolete. That is the reason why you should look for novelties and retrain the models, because as time goes on, time-dependent data and events can change. For this, I want you to look at the outliers on this image, and can someone tell me how many outlier points here are global? It's enough if you raise your fingers. Yes, thank you. Because I wanted to use Microsoft Paint and create beautiful circles. I promised to myself if I will ever have a presentation, I will use Microsoft Paint to highlight the circles. Thank you, my dream came true.
Sorry. Quantum, about 20 about 30 on X and minus 2.5. Isn't it should be yellow also by local outlier?
Yes. You have better eyes than me. Yes, it should be also be a local outlier. But it is dependent on the number of n which we use and the contamination. So this would be a representation if I would use the negative local outlier factor attribute, and I would select the numbers, let's say, from -1 till -1.5 would be the local outliers, and the ones below -1.5 would be the global ones. And you can create, if you need to create more of it, then you have to raise the contamination and just add your labels there. So it is all nice where we can use these, how we can use this algorithm, but where we can actually use it. I have experience in using it for behavioral anomalies. So let's say we have some sensors or we have some data where we have behavioral patterns of someone. We have offices, we have there a sensor like, okay, he is working from 11 to 11.5, or we have monitoring of seniors, for example. They are eating their lunch at 12, something's happening, and they eat their lunch at 11. That may be some concern, or when they are leaving their homes for doctor appointments, or when they are going to look for the newest sales in the shop. Everything is behavioral based. And if we look at human data, humans are really behavioral people, like we like tradition. So we have a pattern of behavior which we use, and if there is an anomaly, then it's easily detectable. But human behavior changes gradually over periods. So you are mostly doing something different every Monday than every Friday. So that is also dependent how you break your data down. You need to use a little bit of common sense if you are using it either on sensoric data, if the workloads are different in different times. That's quite important. If you are using it in fraud detection, then we have faulty emails or bank frauds. That's also used there, but there is a little bit more complex data pre-processing behind it than looking at data points on a 2D grid. Also in traffic anomalies, network security, where we have a different amount of data logs per time. One of my colleagues also had a dissertation thesis regarding network security and looking for anomalies within there, and you can see easily peaks there when someone is trying something which they are not supposed to do, but the problem is that it is quite hard to combine that useful data where you can train the model. It is used in healthcare if we have some sensors or medical hardware on us and we get medical data, then we can see anomalies, how our heart beats, for example, if there is some asymmetry within that or so, and monitoring of machines if we are using something for production or manufacturing. If the heat rises or if there is something between the machine itself, then it can cause an anomaly, and it can be used to prevent some faults with the machines, and they can save money. So it is also used in industry pretty commonly. So what do we need? To do this, you only need data, Python and scikit-learn, and a little bit of insight into data, that with the reasoning, what can I see and what can I use the data for within the scope of anomalies. I prepared a little bit of a hands-on, which is a very long Python code, so I can show you it is very hard to learn.
You need 2 hands for the hands-on.
Yeah, sorry. Okay. Can people in the back see it also? Thank you. So, I used the CSV and imported it via pandas. I'm sure everybody knows this library. And for visualization, I use Seaborn. So we just run it, and I will show you a little bit about this data. It's very complex. Okay. So if we look at it, we have their event type, which can be coffee break. We have a starting point and an ending point. In this way, we have a time series data based on some events. There can be many events. It depends on the use case and how we process it. I took the liberty of breaking the data a little bit down with some cleaning. So I use datetime functions, which Pandas has integrated, and added their day of week, hour, minute, daytime in minutes, and week time in minutes. The last two are dependent on the fact that I want to flatten the data into one-dimensional space. It is a little bit of a not recommended approach, but it can be done. And now if we clean it, we extended the data space, and we can use the new attributes to train the model on anomalies. Okay. I chose number of neighbors 20. Can someone give me a random number? Thank you. Okay, we chose p-value 1, and let's say that 21% of the dataset should be anomalies. Okay. So we didn't leave novelty on because we only have 500 data points, but we could if we would train it a little bit more, but that is for a pretty longer time. We used the fit predict, so we inputted the data, set the parameters, and labeled it. That is just a little function where we label the data anomaly or not anomaly. And I have a problem with my code. Okay.
Where does the label data come from? Is it imported correctly?
Outlier indices, label data. Okay, we can do it a little bit differently. Okay. Pravda, že to nefunguje, keď to testujem? Okay, outlier indices.
This doesn't happen on teleconferences, you know, when you have just a number of people watching. But yeah, the label data was not defined because you probably didn't import it. But where does it come from? Which library? That one. Yeah. Let's Google for answers for now. Yeah. Well, yeah. In the meanwhile, we can ask about some details. Just go on. We do, but go on. Just. Do you want to answer them, or you just like to keep focused on the code. You could mirror this very easily. Yeah. So, there's many methods to identify outliers. In which use cases does this method outperform other methods?
Well, this method is useful when we have a low number of data points and low dimensionality space. So if you are limited with data and you don't really want to use a lot of preprocessing, it's quite useful. If the cost itself and training on low data points is fast, and you can create, if you are using time series data, you can create time thresholds with it pretty easily. It's a robust tool, but it's just one of many in the end.
Thank you. Yeah, okay. You just have to import it from somewhere, the label data, but you would have to find the... Yeah, okay, never mind. So how do you choose the local outlier factor method parameters if the method is unsupervised?
Well, that was the reachability and the local reachability distance calculation. Those parameters, which were the p-value, number of neighbors, they were for calculation of the distance between data points itself, and it decides on the density and the distance between data points itself on the fact that what is an outlier and what is not an outlier. That was the whole reason why I put the reachability distances there and the density of the data points. It looks at the picture as a whole, and what is, on the easy terms, what's more far away from each other, and it is not near many neighbors, is an anomaly, in very simple terms.
Okay, I didn't ask the question. I asked, but... does it take into account any distributional properties from which the data can come?
Nope.
Can this method also deal with multivariate outliers?
Yes, but in that case you need to use the p-value above 3, and it would be good to visualize the data in some bit more complex way, I would say. It is possible to do it. If that was the question, yes, it is possible.
Okay. What is the most misinterpreted aspect of local outlier factor you've encountered thus far?
Well, the most misunderstood fact was regarding outliers in general. When we were discussing use cases for some project, and I said, okay, why don't we take a look at these outliers? They may be useful. I got looks like, why? We have to delete them. So not everybody has a positive understanding of outliers, and they don't view the magic behind it, that, okay, we can create something out of that, and we can use it in pretty interesting ways.
Thank you. Oh, okay. So the paper, not sure which paper, the one that you shown probably, is from 2000, and the same authors developed it further into local outlier probability in 2009. Do you know it?
I heard about it a little bit, but I haven't tried it yet. LOF was enough for the use cases which we used it, and LOP, honestly, I didn't have enough time even to try it. I know about it, but I would need at least a few days to try it and see if it is useful for the use cases which we use it for. If I find something which is useful and it is enough for the purpose, as here there are many developers, I think, or data scientists, we are bound by time and we can't test everything into infinity. So if it works and if it's acceptable, we mostly use it.
Thank you. Can local outlier factor be used to estimate the frequency, magnitude, and severity of extreme weather events?
Yes. Well, as I mentioned, you take the data points, you break that information down in the training set. It returns the values within the local outlier factor, the negative outlier scores. And you can invert them back, and then you can see the thresholds itself. So you can create threshold calculations by result of scores when we are inverting it. And you find the thin line between what is an weather anomaly and what is okay.
Thanks. Any other questions? There is a person showing me that, yes, you mentioned that for calculating distance between points in a two-dimensional space, Euclidean distance is optimal. Do you have recommendations for distance calculating in an n-dimensional space?
The general rule of thumb is not to use the p-value higher than the input dimensional space. So if we have three dimensions, p-value should not be higher than 3. If we are using lower p-values, the results will be better.
For the distance calculation in an n-dimensional space. I'm not sure whether I understood the question. I think they are asking about the distance calculation recommendations. Maybe we can ask also in the public where it is the statistics and probability.
Well, if you're talking in the meaning of this algorithm, it's just a change. It's just a switching of the p-value. Generally, there are many algorithms, but I would use this one for calculating it itself. In my experience, I don't really need just a number. I need to input it into a more complex algorithm. But if you are searching for a recommendation, generally, not really. Euclidean, I generally use Euclidean ones.
Thank you very much. I think we are done for now. How hungry are you? Okay. So, and you can, you had a nice slide about lunch now, so thank you very much.